Welcome to the first of 3 webinars. Today I'm going to be specifically talking about generating a random test using field data. Next week, Tuesday, at the same time, I will be talking about generating a shock test from field data using SRS and user-defined transient. And then the following Thursday, so next week, Thursday, a week from today, I will be talking about a new feature from Vibration Research that is a tool designed around generating a sign on random test. So this is kind of a 3-part series, and today's part will be a little bit of an introduction, and then we will go through an example of generating a random test. I'm not really going to dive too much into the theory. We will do a little bit of introductory and explanation of how the tool set works, but then it is very much going to be a demonstration, and I will walk through a couple of examples of opening field data, viewing it, editing it, and then generating a random test today. And we'll do those same type of examples, very application based, over the next 2 webinars. So to get started, Vibration Research core values: collaboration, capable and competent, accountable and responsible, strong and driven work ethic, do the right thing, and innovation. Innovation is one that really steps forward today, as the features that we are talking about are innovative features that were implemented in software created by Vibration Research, whether it be ObserveView or Vibration View. And we can look at our timeline of innovation. And these really all 4 are designed around running a better test. The first was field data replication, which is a one-to-one replication of field data. So that is, I go out in the field and I want to play that signal back on the shaker. Our innovation was removing some of the restrictions around iterating these pulses or iterating these playback waveforms and the length of the waveform that we were able to play back. Next, we have Kurtosion. We will talk a little bit about Kurtosion, specifically today in regards to what do I do if the environment that I am trying to create a random test for is non-Gaussian. And the real world is very non-Gaussian, so we have to take that into account when we create the test. And we will address that on a couple of fronts today. Next is fatigue damage spectrum. Fatigue damage spectrum is the tool that we are going to use to develop a random test today. So we will be talking specifically about fatigue damage spectrum. And then the last innovation is IDOF, or instant degrees of freedom. This is a method of smoothing the control lines, or being able to display a PSD, power spectral density graph, with much higher lines of resolution, or excuse me, with much higher degree of freedom than what is statistically possible through normal PSD estimation methods. So IDOF is that smoothest control lines in the industry, and we will look into that as well today when we start running our random test. So as an introduction, I just want to talk about generating tests based on real world data. And there are a lot of methods available for this. First is field data replication. I talked a little bit about that in the innovation slide. But field data replication is a one-to-one replication of field data, meaning I go out and record a time history and then play that back, typically filtered in some way, on a shaker. I would filter it to minimize the extreme high frequency content to the frequency range that my shaker can handle. I would filter the extreme low frequency to minimize the displacement so that I can actually run this on a shaker. And then we also have the ability to add custom notch features that are live adapting and can be added and removed while the test is running. The next two tools, random import and fatigue damage spectrum, are a part of the conversation for today. We will mostly be concentrating on fatigue damage spectrum. The random import tool utilizes some older methods. It uses either a peak hold or an average. And the problem with either of those methods, peak hold or average, is that I either end up overemphasizing my peaks because my real world is not perfectly Gaussian. So if I do the peak hold on a non-Gaussian real world environment, I end up overemphasizing those peaks and the random PSD that is generated is over testing. Or if I do the average, I end up under-emphasizing those peaks and I end up under-testing. The other problem with this random import tool or with the random import methodology, not even our tool, it's just the methodology in and of itself, is that it typically only applies to one waveform at a time. I can do this analysis, generate the PSD for that one waveform or single environment, and then repeat this process for multiple environments. And in the end, envelope them all together to get some maximum value, but it still doesn't give me a method of properly accelerating the test. It doesn't really work if I have a 10G RMS random test that is generated from 20 to 2 kilohertz. I can't double my RMS value in half the time. That relationship is not that correlated. So we need to use a different method of analysis when we want to accelerate the test. And that's where fatigue damage spectrum comes into play. The fatigue damage spectrum, there are a few methods that we will talk about, and we will specifically discuss the method that is implemented in VibrationView for analyzing a series of environments or a series of time history waveforms, accounting for the non-Gaussian nature by analyzing them in the time domain rather than the frequency domain, and then converting them into a fatigue damage spectrum where we can use that combined fatigue damage spectrum to appropriately weight different environments, and in the end, combine those environments so that we can generate a damage equivalent random PSD at the end. The next two are shock response spectrum and user-defined transient. These are used for analyzing and generating complex shock tests based on real-world data. There's also a whole other industry or several other industries that use this for shock testing and for using something other than the classical shock pulses. So we use this to generate and, in the case of next week, Tuesday, replicate complex transients in a controlled manner. And the last icon that you see there on the bottom is sign tracking and analysis and generation. I have my words messed up in the bullets, but it's sign tracking, analysis, and generation. This is a new tool that will be released from Vibration Research in the next couple of days that allows us to analyze an environment that has a strong rotational component that needs to be replicated in testing as sine tones. And we have the ability to analyze the environment, extract the order or rotational content out of the time history waveform, generate sine tone profiles for those rotational components, and then use the remaining content after the orders are extracted to generate a random test. So we have two parts there. One will be a duplicate of the fatigue damage spectrum to generate the random portion, but then we have a new tool that allows us to extract and generate an accelerated sign test. And again, that webinar is going to be next week, Thursday. those are the tool sets that we are going to be using through this series of webinars. And I want to get started with fatigue damage spectrum. So I have a few slides here that talk about what fatigue damage is, how it is calculated, and how in the end we end up generating a random test. That is the overall goal of this process, and I will step through a demonstration where we actually walk through this and can use some real world data that we'll look at and then use that to generate a FDS test, a random test in a few different methods. So the first question that I asked was, what is fatigue damage spectrum? And this mentality is something that you have to wrap your head around. We're not trying to replicate an instantaneous shock or the shattering of glass. The fatigue damage failures that are being replicated through this type of testing are high cycle fatigue tests. The easy example is a cantilever beam that I might have mounted on the shaker. If I find the resonance of that cantilever beam and run for a period of time, how long does it take for that beam to fail, to actually develop a crack, or simply not have the mechanical characteristics that it had at the start of the test? So there's all kinds of theories behind this, but in the end, damage is accumulated based on repeated stress load. And if I apply that stress load at different values, it will take longer or shorter periods of time depending on how much I excite, in this example, a cantilever beam. So if my cantilever beam has a resonance and I dwell at that resonance at 1G, it's going to take longer to fail than if I dwell at that resonance with a 10G input. And one of the tools that we end up developing and using later on in the FDS test development tool is an SN curve, or stress to number of cycles to failure curve. And this can be developed, it can also be estimated. And in the end, the slope of that curve determines the material property that we need to enter into VibrationView. So here I have a series of tests that I ran on a cantilever beam. In this case, when I started at the top, you can see I had a stress level of 5.2 Gs RMS, and my time to failure was 2.7 minutes. And as I decrease the overall RMS, or the overall stress level, it takes longer and longer for that beam to fail. If I continued to decrease the stress level, eventually I would reach a point where really my product is never going to fail. But that slope from highest stress level to lowest stress level with a failure is what I'm going to use in the FDS process. How is the FDS calculated is our next question. And one of the first things that we do is take an acceleration, time waveform, or velocity, or displacement, doesn't really matter, and import that into VibrationView. VibrationView automatically converts that either through integration or differentiation into velocity. And the reason we use velocity is because velocity is very proportional to stress. So that velocity measurement, or that velocity time history file, is run through a series of single degree of freedom oscillators. And you can see some examples on this slide where they're each highlighted in their own color. So the red oscillator is a 20 Hertz oscillator. And when I pass a waveform through that, the output of that theoretical oscillator is all of my 20 Hertz content for that entire waveform. And I repeat this process at defined frequency intervals so that I end up with a series of single frequency or very narrow frequency waveforms that I need to analyze individually to calculate the amount of damage that is done at that particular frequency. So I take my single or narrow frequency band waveforms and utilize rainflow analysis and cycle counting to essentially give me the number of peaks that occur at a particular amplitude for a particular frequency. Knowing that information, I can pass it through my damage calculation, which is cumulative damage based on the SN curve and results in a arbitrary damage number for that frequency. The damage number really doesn't mean a lot unless I am doing comparisons between multiple environments utilizing the same analysis or FDS generation parameters. So as long as I'm using the same analysis parameters, I can compare in the damage domain. Once I have a damage number for that frequency, move on to the next frequency all the way through my analysis range and end up plotting that on a graph to give me a fatigue damage versus frequency graph, which is that fatigue damage spectrum. This process is entirely automated in Vibration View, and we will see that once we get into the example. Once I have a fatigue damage spectrum, I need to convert that into a PSD. And some gentlemen by the name of Henderson and Pearsall came up with a conversion originally designed to convert from the PSD into the FDS for purposes of test acceleration. Now, the flaw in that methodology is that conversion assumes that the data, that the PSD is Gaussian in distribution, or that my peak distribution is within plus or minus 4 to 4.5 sigma. My real world data in many cases is not Gaussian. It does not follow that nice bell curve in peak distribution. So the problem that I run into is if I would analyze my field data using, say, average or peak hold import tool and turn that into a PSD, then convert into a fatigue damage spectrum using this method, then try to sum them up and accelerate the test in the damage domain, I'm not accounting for the non-Gaussian nature of my real world environment. Because of that, I'm really not running an appropriate test. If you saw in the previous slide, when we do this in Vibration View, we are analyzing every peak to valley stress cycle in the time history waveform and weighting it appropriately through rainflow analysis. That method allows us to account for any non-Gaussian peaks, any non-Gaussian nature in the field data, so that when we do generate a PSD from the generated fatigue damage spectrum, we've already accounted for the damage caused by those higher peaks through that, again, rainflow analysis. So we could run a damage equivalent Gaussian distribution test, even though the real world data is non-Gaussian. There is the option, which we'll see here in a minute, in Vibration View to add kurtosion, which is Vibration Research's patented method of kurtosis control. Kurtosis being that characteristic that allows us to modify the peak distribution of our random waveform. So I can make that waveform non-Gaussian through the addition of kurtosis. So we can add kurtosis to the test, and the goal is not, in that case, is not going to create more damage. We're looking for damage equivalency to our real world environment. So adding kurtosis is not going to generate more damage. What's going to happen is when I add kurtosis, the overall GRMS level of my defined test is going to decrease to account for that increase in peak acceleration. And in the end, the reason for adding kurtosis would be to have peak accelerations and a peak distribution similar to that which the product would experience in the real world. So it's all about real world equivalency, not necessarily about creating more damage, because we are actually decreasing the overall RMS value of the test to account for those added peak accelerations. So when we have our FDS generated, we utilize the Henderson-Pearsall conversion to convert from the fatigue damage spectrum into a PSD. And that is the method that is used for generating a damage equivalent random test that can be the combination of multiple environments scaled appropriately to their contribution to the lifetime of the product, and then accelerated to run that life dose worth of damage in a much shorter period of time. So that is the theory kind of introductory portion of the webinar. Next, I'm going to jump into our VibrationView software and ObserveView software and actually walk through an example of me creating a test, and we will just go step by step and walk through this process. So the first thing that I'm going to do is actually open my time history waveform, a time history waveform, just so that we can see what it is and talk about what I may or may not do to this waveform in order to prepare for generating a test. So this data is quite interesting. The software package that I'm using is ObserveView. It is our analysis software. We are developing more and more tools for this, and you will see some of those tools that our development team that has been working on next week. In this case, I'm going to open the time waveform, which I have here, and I can do a few things just to get an understanding of what this environment is. When this data was recorded, it is a mountain bike set of data. If I click replay, it actually has GPS data and multimedia data that is attached to and saved in the same file location as the time history. So I'm just going to move these up and down for the sake of my internet connection. We are going to run these on a little bit lower frequency resolution, the videos, or excuse me, lower screen resolution. And we can look at a couple of things. First of all, if I zoom all the way out on this waveform, I can see in my GPS map how fast I was going for these different points. So here's if I click on it, it will actually snap me to that location. But if I hover over one of these, I can see that Aaron was riding at 15.19 miles per hour there. And some of these other spots, a little bit slower. I can look at the GPS map locations, and this is obviously just a bicycle ride, so it's not quite so far of a distance, but I do have data that goes from Grand Rapids, Michigan, all the way to Northwest Iowa, and you can see how fast or slow we were driving throughout that entire range, and it really helps snap to different locations. We also have a couple of video cameras that were attached both to the bike rider and to the bike in itself that are synchronized with the playback of my time history data. So here I can hit play, and you can see, we'll mute Aaron here so we don't have to listen to him. But you can see the video data and GPS data all synchronized together as I play through this waveform. It's just a great way of, if I want to look at a particular peak here in the middle, I can see that this peak occurred at this particular location, and I can maybe watch the video and see where that might have happened or what I might have hit or run across. That would give me a little bit more insight to what is happening. So for our test development, I went ahead and exported this waveform to and a series of other mountain bike data sets that we have. And I just took the first 3 channels just to simplify our analysis. I did that by going into File, Export, and here I have the ability to resample, filter. I could add a notch filter if I wanted to. And I just exported these 3 channels. And I did this for all of the different mountain bike data sets that we have. So we're looking at just the fork vibration in all 3 axes. So that is just a basic analysis walkthrough. I could do a little bit more if I wanted to. I could add a graph and create a PSD. This would be a linearly averaged PSD using, get rid of these, move this over so everybody can see that. So using the analysis options that I have here, so 8192 lines, Blackman window function, and that is my PSD analysis parameter. So that is one method and essentially would be the same as the average import method of PSD generation. So I had one question come up, how was this data collected? We have an Observer 1000. It is Vibration Research's 16 channel battery powered data acquisition hardware. It's also a dynamic signal analyzer, so you can do live analysis with it. But this is 16 channel battery powered, has integrated IEPE power. You can connect dual TAC as well as GPS to it, and it records to an onboard SD card. All right, so I have done my analysis and I actually went ahead and exported all of these environments that we recorded to their own files. So now I can go over to Vibration View. Just wanted to show this as an introductory cursory glance at the data that we're looking at and show that this is real data and we actually went out and recorded this. So it's just good information to know. All right, so next we are going to go to Vibration View. And in Vibration View, we are actually going to walk through and create a new test using the fatigue damage spectrum. And we're going to combine, I think I have 10 different environments that we will combine together. So I'm going to start with new test, and we are going to use the fatigue damage software tool. And this is the tool that we want to use for developing our random test. This takes me to an import tab where I can analyze a single environment, but in this case, I want to do 10 different environments. So I'm going to use the FDS Combine tab on the right-hand side. FDS Combine, I can add items. Items would be the recordings or the time history files that I want to analyze. And for the sake of time, I'm going to pick, we'll just do the first 5. And if I click open, it's going to populate those for me. And I can see that I have fork, Z, lateral, aft. And for each recording, I have 1, 2, 3, if I scroll down a little bit, 4 and 5. I have my 3 acceleration channels for each of those environments. So the next thing that I need to do is verify my fatigue damage settings. I'm going to use an M of 6. This number is based on the SN curve. So I can use a generic SN curve, or I can pick something specific. Mil Standard 810 says if you don't know, use 8. In the end, it really depends on the materials that your product is made for, and the material property is typically designed around metal fatigue and metallic fatigue. Q, typical settings are 50. We will see the effect of changing the Q here shortly. I'm going to generate a test that goes from 10 to 2000 Hertz, and I'm going to use 1/24th octave spacing. I also have the option to do Hertz spacing, so if I did want to have 1 Hertz resolution or 10 Hertz resolution, I could use that as a smoothing factor for how my PSD in the end is generated. We're going to click Scan Items. So this Scan Items Now Vibration View is going through that FDS process where we are converting that waveform into velocity. We are passing it through that series of single degree of freedom oscillators. For each narrow band or single frequency waveform, we are doing our rain flow analysis and cycle counting to generate the number of peaks that occur at a particular amplitude for a particular frequency, then running that through our damage calculation. And the end result is this information at the top of my screen. And I can see for each one of these waveforms, if I click on them one at a time, I can see the fatigue damage spectrum for each of those environments and see how that all overlays. The next step is the actual test development portion. And I have a few choices that I need to make. Excuse me. So I have a few choices that I need to make. I need to determine the target life for each of my environments. And that target life is going to be the ratio to which they are contributed to the end result of the test. So if I have one environment that is 100 hours of my 10,000 hour life, and I have another environment that is 5,000 hours of my 10,000 hour life, they're going to be weighted appropriately and passed into the end calculation appropriately, so that when I generate my damage equivalent test, each of those environments has their appropriate contribution to the end result. And I can also combine these in different ways. If, for instance, I wanted to do multiple environments that were all a portion of my end use, as I've been talking about, I would do the sum combination method, meaning in the end, each of those environments is some portion of the total lifetime, and the total sum of damage is what I expect my product to be exposed to throughout its life. So I want to sum those together. Another option would be to envelope. This is, rather than making it a cumulative damage, it is just enveloping all of the damage from all of those files and giving me the envelope. The last one is per file envelope, and this is the one that I often end up using, especially when developing a random test where I don't necessarily know the axes that my product is going to be mounted in all of its environments. So what I do is I go out and record all of these different environments and then use the per file envelope. So what that is doing is enveloping my 3 channels, X, Y, and Z, together, and then summing each individual environment. So I'm summing environment 1's envelope with environment 2's envelope with environment 3's envelope to get cumulative damage for the envelope of each of those environments together. Once I've picked a combination method in the lower left-hand corner, I now need to set my target life contribution for each of my environments. So let's say my product lifetime is 5,000 hours for this bicycle, for the fork of this bicycle. That's how many hours I expect to get out of this. So I might make this particular recording 2,500 hours. And you can see as soon as I change that value, it changes the FDS in relation to all of the others. This second environment might be 500 hours. My third environment might be 500 hours. And if I continue to scroll through here, I can do 500 hours. And I said I wanted to do 5,000 hours, so that means my last one has to be 1,000 hours. I'm just entering that target life in the box on the right-hand side, and that is setting the percentage, or how much of my total target life, which you see down here at the bottom, that waveform needs to represent. When I look at these, I can see what my end test result is, in this case with no test acceleration applied. So my test duration is 5,000 hours. My total target life is 5,000 hours. If I were to run that test, I would need to run a 3 GRMS 0.46 inch displacement peak to peak test for 5,000 hours to replicate that damage. Now I can accelerate this. Let's say I want to run this test in 72 hours. As soon as I type that in, you can now see the change that was made to my overall RMS value, the displacement, and the velocity. The next question that we often get is in relation to this Kurtosian time compression at the bottom. And as I talked about in the introduction, adding kurtosis, or modifying the distribution of peak acceleration, which is really in the end what we are doing, the main goal of that whole process is to have similar peak accelerations to what my product experienced in the real world. And a simple way of seeing that, if I actually hover over this RMS, I get some statistics for that particular waveform. If I move down, I can see the next one. This one had 0.39 G peaks, but had a kurtosis of 14.8. This one had a kurtosis of 19.1. It's kind of in the middle of this 13.1. I can see all of the acceleration, velocity, and displacement. So let's say I want to add Kurtosion. As soon as I click this checkbox, what you're going to see is my overall RMS is going to decrease. If I check that checkbox, I went from 6 G's RMS down to 4 G's RMS. And I can modify this. Let's just say I wanted to do a kurtosis of 13. Again, it's modifying the end result as I manipulate this value. From here, I have done my analysis. I have set my target life. I have set my test duration. I have added my kurtosis. At this point, I'm really ready to create my table and see where I am at. And I can do that by clicking the Create Table button. That Create Table button is going to generate excuse me, a PSD. It is also going to apply that PSD to my table tab. So this is the PSD that I generated. You can see really above 100 Hertz, I don't have a whole lot of content that is worthwhile. So if I were actually going to design and run this test, especially at the bottom of the slope, I'm probably just going to get rid of this because I just don't have any useful content above 2000 Hertz. If I look at my test schedule is set to run for 72 hours, which was my set to test duration time. And on the parameters tab on the right-hand side, I have my Kurtosion already configured to that kurtosis of 13. Now, one point that I do want to make here, if I am looking at like a bicycle environment, those high peak accelerations are very random in rate and amplitude. So I have these two sliders at the bottom of my Kurtosion test definition that allow me to change both the rate and amplitude of those high kurtosis non-Gaussian peaks. If I were trying to replicate something like an engine environment, if you think of a diesel engine, they have very, very high kurtosis, but those high peaks are very repeatable and happen at very, very defined time increments. So what I might do for a diesel engine, rather than having the rate and amplitude be variable, I would want those to be very constant, because that's how an engine works. Then I would need to modify the transition frequency to be related to the time frame of my cylinder impacts or whatever I was trying to. So if I'm at 100 RPMs, that could be converted into frequency, and I could enter that value here and figure out how many cylinder impacts I have per revolution, and I could figure out all of that math if I chose to. But that's just one quick note about variable rate and variable amplitude. It depends on the environment that you're trying to replicate. If I'm a car driving down the road and I'm hitting potholes and bumps, that again is going to be variable rate, variable amplitude. But if I'm an engine mounted component, my kurtosis peaks are going to be very constant. So that's just something to keep in mind. From here, I can click OK, can save this test. That test can be sent to any of our controllers and opened and be ready to run. You could also use this to generate your own test specification. I can simply right click on this, copy the profile to the clipboard, and then go to Word and just paste that right in. And there I have a lot of breakpoints, but I have the table at the top, or the graphical display at the top, and then my long breakpoint table with the test duration. So something as simple as that works that well. So that is just a quick example of walking through generating a random test with the fatigue damage spectrum. At this point, I'm going to open it up to questions. It looks like I have a few, and I will answer them. If anyone else has any questions, feel free to enter them in. May I use any DAC system? So the answer is yes, as long as it has some way of converting to a generic file format. So you could use any data acquisition system as long as you can output a file that is text. There's all kinds of options. If we look at field data replication, you can see UFF, text, WAV, RPC, any of those generic file formats, as long as you can import or you can export to that, then we can use this as you can convert those files into a fatigue damage spectrum, and then, you can convert them into a VFW file, which is our proprietary format, and then do that same analysis. All right. What are some examples of real life factors that help you determine these target lives? That's a great question. So if you look at like automotive companies, they know what percent, they have estimations of the test track data and what contribution that has to the lifetime of the product. So they know that 20% of the lifetime of the product, it is going to be on rough road, there's 10% on Belgian block, there's 40% on highway at high speed, whatever it might be. But uh, there are existing estimations as to how components are exposed to different environments throughout their lifetime. But in the end, it really comes to an understanding of the end use of your product and a knowledge of how your product is being used. So it's so much different for every product that it's really hard to give a good determination. If we do not have the Kurtosion tool, I'm assuming we cannot add kurtosis into the FDS. That is correct. You would need to have Kurtosion in order to add the kurtosis. Doesn't need to be Word or can use Google Docs. You can use Google Docs, you can use OpenOffice. We're just copying it in a text format and you can paste it into whatever you want. How did I incorporate the bike video with the vibe/tack data? So that is a feature of ObserView. We use the timestamp from, in this case, 2 GoPros to incorporate the data. So the data has a timestamp attached to it, and the Observer 1000 has a timestamp attached to it. And the GPS data also has timestamps associated with it. So we are aligning that data via the timestamp. And the best way to do that with the GoPro, if you connect to a GoPro with your phone, you can sync the time data with your phone time. And you can also sync your Observer 1000, our data acquisition time, with your phone time via our VR mobile application that runs in the Observer 1000. So it's all time synchronization based on timestamp of the data. How many numbers of frequency we can add in a random test? So in Vibration View, newer versions of Vibration View, you can have up to 10,000 breakpoints in your random test. Next question, what effect does Q value have on the data? I assume we would get this from the product or a sign sweep. So yes, the Q value, if we go back to Vibration View, we can reprocess this data with a different Q. And what I'm going to do actually, we'll do a new graph, FDS, and we'll take just this environment here. And I'm just going to drag these off the software and create a static copy of these fatigue damage spectrums so that we can see them later. So I just did the first environment and the combined. Now, if we edit our test, go to combine, I can change the Q. Let's just go to something lower, so to 5. If I rescan this data, it's going to change the filters, essentially, the single degree of freedom oscillators, so that they have a different quality factor. So it's that in the end is what the Q value is setting, is the Q of the single degree of freedom oscillators used to generate the single or narrow frequency waveforms. That affect, this whole calculation operates under the premise that there is a resonance at each frequency. So if you can see that after I change this, we'll just do there we go. So you can see that after I changed my Q, if I look at my combined original with the higher Q, it's a lot rougher. It also is higher in amplitude because that Q is more appropriately aligned with the resonances and gives me a finer definition. But my ending PSD is much smoother for a lower Q value. All right. Basic question, what makes this a random test? the fact that we are controlling in the PSD domain, and when I click start, so when I click start, the waveform that is being generated, the time waveform, if I click edit graph and insert, we'll look at the time data as well. You can see that my input waveform is random, such that, and we're shaping that random output. So in the end, the averaged data plotted in power spectral density, G squared per hertz, matches this profile. So the overall amount of energy at each frequency is what we are modifying to meet that demand profile. All right, bring up my questions here. Is there a best method to increase G level to reduce time? In a random test, this is the best method to increase the G level to reduce the test time. And you can see that if I go back to edit test, go to FDS combine, when I change my test duration, let's say 1,000 hours, it's going to change my overall GRMS. So this is really the only way to properly accelerate a random test. Now it is a little bit different in sign, but the best way to do it for random excitation and for a random environment would be through this A fatigue damage spectrum tool. I think that is all the questions that I have right now. I'll be on for a few more minutes. If anyone has any more questions, please feel free to type them in. I will answer them to the best of my ability. Otherwise, make sure to tune in next week, Tuesday at 11 a.m. Eastern Standard Time, where I will be discussing generating a complex shock test using real world data in the shock response and the shock response spectrum. I actually am going to have another demo very similar to this, and I think I will actually record the data live as well so that we can take a look at that. So I will have a tool. I think I'm just going to use an impact drill, something that has and drive some screws into a piece of wood, and we will take those time history files that we acquire from that, analyze them, use SRS to develop an SRS envelope for a series of tests, and then use that and one of the original recordings to develop a appropriate SRS test based on complex shock data that has the same or very similar frequency response to what was seen in the real world. All right. I had one more question come in. Why not have time-based data replication itself rather than convert into a converting PSD? Okay, so time-based replication, yes, is valuable, but you can't really accelerate it. So the issue that the benefit of converting into random is one, it randomizes everything, so it's a little bit more generic than a specific environment. So you're getting a random excitation with the same amplitudes or similar damage to what your product saw in the real world. The other issue is if I have to recreate 5,000 hours worth of life, I really don't want to run a test for 5,000 hours on my shaker. I would much rather replicate that same amount of damage from all of those time waveforms in a much shorter period of time. Now, that said, there still is value in doing data replication. It does show you how your product will respond to that real world vibration. And there's a lot of engineering conclusions and a lot of information that can be pulled out of that. That is very useful. But in the end, it just depends on what you are looking for. All right. Seems like this data starts at 10 hertz, was trimmed out. Let's say we have field data going down to 1 hertz, maybe hitting displacement limits. Yeah, that's the problem with, so this test really would probably be one to, let's just rescan this data a minute and I can show you the answer to that question and what the end result is rather than walking through it and trying to explain it. At the end of all the analysis, would you simply reduce the number of breakpoints in your PSD? I could reduce the number of breakpoints in my PSD, but I don't have to. In this case, it's already in vibration view. There's no reason not to run it with all of those breakpoints. The only reason you would want to is if you were trying to enter it into somebody else's controller, which would make for a lot more work. So then, yes, you could reduce, or you could use some of the, either change the spacing of your frequencies or change the Q to develop a smoother PSD. All right, so back to the question about displacement. Here is a great example. This data, if I create the test, you can see if we look at the PSD that's generated for this, I changed my analysis parameters. For, in this case, a bike, most of my vibration is going to be in this extreme low frequency range from 1 to maybe 100 hertz. In this case, really, if I have a resonance here, I might be concerned. But if I don't have a resonance, I'm not going to damage, that's high cycle fatigue designed around high cycle fatigue failures. So minimizing the amount of displacement you have to do by reducing or removing that low frequency content. There's no, I'm not going to get damage replication if I am reducing these peaks in any way. So this is the amplitude that if I want to run this many hours of damage in this period of time, this is the amplitude that I need. Now, the other option is run it on a hydraulic shaker. 8 inches of stroke is probably a little bit much even for a hydraulic shaker, but I could probably crop, let's just say my first point is at 4 hertz, and now I'm at 1 inch of displacement. So removing the extreme lower frequencies is the way to get around those displacement requirements. All right. when you remove content below 4 hertz, is the missing damage spread out the rest of the frequency range? So that's the interesting. So the damage that we are looking at is specific to each individual frequency point. Really, it might be more clear if we looked at this rather than a line, a whole bunch of vertical arrows. So each one of these individual points has a specific damage number. If I cut out the frequency content, I am just replicating the damage rather than from 1 to 100 hertz, from 10 to 100 hertz. So the damage numbers, it's really pseudo damage because it's assuming that you have a resonance or a natural frequency of resonance at this point. And in reality, if you do not have a resonance at this point, you're not accumulating damage at that point. Your product isn't going to fail if it's not resonating at a specific frequency. So yeah, when you remove the content below 4 hertz, the missing damage isn't really missing. I'm just making the assumption that I don't have a resonance below that frequency, and therefore there isn't. For high cycle fatigue, I'm not missing anything. Damage is proportional to the number of cycles at a particular amplitude for a particular frequency. So the question is damage proportional to the number of cycles? And the answer is yes, based on the slope of my SN curve and, again, the amplitude, the number of peaks at a particular amplitude for that particular frequency. Not necessarily generic cycles applied, because if I have a resonance at 100 hertz and I run 10 million cycles at 100 hertz versus 10 million cycles at 800 hertz, my 10 million cycles at 800 hertz really isn't doing any damage to my product if I don't have a resonance there. My 10 million cycles at 100 hertz is going to do an exceptional amount of damage at that frequency. All right. And that is the end of my time. If anyone has any additional questions, let's look at the presentation here and make this big. So again, next week, Tuesday, is generate shock tests. The following Thursday, 30th, will be generate sign on random tests from field data. And if you have any questions, feel free to reach out to vrsales@vibrationresearch.com. Obviously, we are all working from home right now, but we are still here to support you and here to help you in any way that we can, help answer as many questions as we can, and do whatever we can to help. I hope that this was informational and educational and useful. If anyone, again, has any questions, feel free to email them to vrsales@vibrationresearch.com.